So welcome back to Extremely Open Science. So just setting up, have my coffee here, and yeah, we're gonna pick up where we left off, which was to looking at these genes that seem to be outliers, but maybe they're not. So just to do a quick recap of what we left off. So, and also just for me to get back into it. So this is our project Sardine. We cleaned up a little bit, and what we did last time was stream notes. What we did that time is that we looked at these genes within E. coli that were outliers. So even in the supposedly highest quality version of E. coli, so they are probably real, and there was actually one of them that had a very clear hit. Whoops, did something go wrong here? Oh, sorry. Very clear hit. This K024336, where every other copy that we have in GMGCV1 is at least 227 amino acids, but the E. coli hit is much shorter with 148. And actually the 148 is part of the database because we are using the E. coli genome. So today I thought we would look at the same phenomenon in some of the other genomes that we've been looking at. So let me just change so that we have the right screen. And so previously we were looking only at E. coli. So and so let's do that. Let's look at the other outliers in the other genomes, and also perhaps think a bit about what we could do with this. Because one of the ideas that we had at some point was this one, to filtering by the position on the alignment, but that's not going to work, at least in this case, because this 148 is actually aligning to itself. So let's just go ahead, get started. So everything here is exactly as before, and we've been looking at this length. Oh, let me just update something real quick. So we know. Okay, and we'll update this. Okay, so I'm just gonna run this. So this is the code we've been running the whole time. Loading the GMGC annotated. So this was all data that we pre-computed before, and the scripts for pre-computing this are here as well. So run GMGC diamond. So so this takes a while. So this is why we put it in a separate file, and then now we've been looking at the output. So get the KOs with at least minimum number of unique genes so that we can do a little bit of stats. These are very few, actually, I think that. So, all right, give me 1 second. Yeah. Stat, and let's just see. So when we do this filtering, okay, so mostly we keep everything, maybe a couple of thing, and then probably this feels like this could be done in polars with a single expression. this feels like this could be. Actually, since we are here, polars group by return list. All right, group by maintain. Well, the problem is it kind of returns a ragged, maybe not. Because the problem is not aggregator. Oh, but maybe. Does this work? This does. Yep. Does this work? Yeah, this works. Okay, I don't think this actually makes it that, and it's not particularly faster. Okay, let's forget about that. That would be. This works perfectly fine. All right, so okay, a little bit of a detour, just looking at the number of sequences. Okay, and this is what we've been doing the whole time, looking at this. We've looked at E. coli, we were looking at these ones, so right, so this table, so this is E. coli, and then here we're looking at 0 mutation, so this is the reference genome. The reference genome from E. coli is probably as good as it is, so maybe the annotation is not perfect, especially with the methods we're using, but the genome itself is probably as good as it's gonna get. And then here, this is, so if you have the sizes Z scored based on the GMGC, so it has a couple of genes at -12 Z score, so that's not great. So these were the ones we looked last time. So Bacillus subtilis, no genes that are that. Lobacter. Okay. Okay, so actually this is, okay, I was saying we should look at the But this seems to be an E. coli only phenomenon. So, okay. Okay, let me, it's telling me, alright. Okay. Okay, sorry, let me just see, playing. Okay, and so, interesting. So it's actually, let's save this. Okay, so the first conclusion is that it's actually E. coli is the only one that's, E. coli is the only one that's different. Okay. Interesting. So I had already noticed this last time. Is that it's actually, and we've mentioned this, is that this is actually this middle range where we see the biggest shift. So this middle range, like -6. So again, in E. coli, there's in E. coli we have this. Let me look at something a little bit different. So we had noticed this KO that we had looked at last week. So KO 2436. Okay, this is no longer KO 2436. What am I looking for? Databases. Check M2. Yes. No. Sorry. I remember. I wanted to check whether the size distribution of this in the size distribution, not in the GMGC, but in the database that we use, yes, this is what I wanted. In the database that's being used by CheckM2. Okay. Which is Unira. Okay. Okay. Okay, there it is. Okay. Okay. Just check. Okay, I'm just gonna start typing here. Sorry, I'm just gonna start. Okay, so let's do this. And I said 2436, right? That was the... Okay. 24. Okay. Okay, so we have this. So is my chair dropping a bit? Yeah. Okay, so 2436, and we see it. So in the Uniref 100 database that CheckMT uses, see, there's an even smaller example with 71 amino acids. You know, that's really small protein territory there. So that's probably not this. Probably not the same. 2436. So we had. Have we looked up what 2436 was? Yeah. Probably not this. Yes. I don't know why I have Spider open here. Okay, 247. I'm not sure that this is helping. A little bit stuck here, to be honest. I'm not sure. I maybe. Alright, let me. So let's. So this analysis that we've been printing, let's save it a little bit. Let's do. Sorry, I'm a little bit fresh. Okay. Okay. Okay, okay, PL concat does not work if there. Okay. Combines frames up horizontally to determine the common key columns and aligning rows using. Okay, welcome. Yeah, hi, thank you. Welcome back. Welcome back. All right, so as I said, I'm a little bit at a loss how to proceed here. I am okay. I do think, however, that this okay, so I would call, let's say, okay, so all right, so minus 10, several of, all right, let's look at the minus 10. So this corresponds to genes that are 10, no, that's not true. Oh yes, it is true. So 10 standard deviations below, I don't know why today I'm a bit slow. 10 standard deviations below what would be expected in these genomes, and it seems that all of them have it. All of them have it. Yeah, I was actually just thinking that maybe what's characteristic of mutations is not is not a particular. Okay, so I was thinking. So until now, I was a little bit implicit in this line of thought. Is okay. If we find maybe we find a good threshold here, where I say, oh, look, we set it at -8, and if it seems that there's 12, that's obviously bad because it can't ever be 12, right? And in this very small data set, it would be absolutely true. But maybe E. coli has 5, but we would find some thresholding thing here, and we're seeing, okay, maybe it's actually this sort of middle range, like -6, where we have there's, but it's still hard to find a good threshold, because right here E. coli already has 9. It's actually weird that E. coli has actually maybe that might be a bit of an artifact of how we're doing things, but E. coli would have 9, but okay, so let's set it at, say, 15, and then maybe we would miss this column here, unfortunately, but we would get that one. And this is how I was thinking about it until about 5 minutes ago, or until it's good to try to find some way, and now what we've been trying to do in the last several sessions is maybe find a way to clean these up. Maybe maybe this is some of these are artifacts, and we could clean this up, and as long as this number here goes down faster than this number here, we would be fine, right? Because let's say that here half of these are artifacts, this will go down to 4, and then, but here only a handful will be artifacts, so this will go down to, let's say to 35, and then we would be increasing the gap. And so we were looking for things like, okay, maybe some KOs have very unstable sizes. Those are not good. And so this is what we were doing. But now I'm thinking maybe it's not what I should be looking at is not the all right. It's not a value, but this curve. How fast does this curve go down? And by looking at this curve, maybe that's how we get it. So, right. So, I'm not sure. So if we do this, let's do something. Let's do this. All right. Okay, it's still not. Okay, maybe not as simplistic as I would thought, but maybe this is getting a little bit closer to what I was hoping for, right? So let's do something like this. Okay. Awesome. Again, the 1,000 mutations, pretty good, but not. But the 100 mutations still very difficult. So very difficult. I mean, maybe we can do. So if we have 100 mutations, let's do a bit of math. So 100 mutations. This model is not great, but 100 mutations. We have 100. Let's say that 100 times we interrupt the gene. Or we have 100 hits on a gene. Well, bacterial genomes are what, about 80+% coding. So we have 80, let's say 85 times we're inside a coding gene, and then how often do we interrupt the genes? So if we're maybe it's only the 30 or 40 times. We could do, that's 30 or 40 times that we have broken genes. So it's not a lot to work with. Nonetheless, so this is something, right? This is something. I'll watch something like this. Group by tag. Okay. Tag. Okay, I don't know what this is. sorry. Okay, something like, okay, what if it's something? Okay, the other way we could do it is a little bit what Checkm2 actually it does itself, which is we take this as input data and then we learn the model. Okay, this is all right. This is pretty terrible. All right, right. What? Let me just look. All right. What we're talking about here is, right, this was a pretty hacky version of integrating, like doing the integration of here, so the area under the curve on this side. But if we look at, right, so if we do the, which is probably, and probably right here, I'm trying to say that, the difference between this blue and this orange line is probably very, very slight. And probably the best we can do is get this green line. But, if it's the area under the curve, this might work. Might work. Still interesting that E. coli, yeah. I know that. Sorry, let's see. Okay, let's do, okay, so we have here the z-scores. Okay, this might actually work, so let's see. I know, so if I do what if I do something like this? Filter. Okay. What about just this? The average, is this terrible? Okay, this is terrible. It's not the average, it's the sum. All right, let's do this. Let's say this is the metric I am going to implement. It's the sum of z-scores below -4. Right? Well, what's wrong with this? Right? Sum. Okay, a minute. Okay. Proposed metric. Sum of these scores for inside. Okay, below a certain threshold. Okay. Okay, let's call this, I don't know. We need it. We need a good name. All right. Let's see what Copilot gene size stability score. No. Normalized excess. Okay. Excess of short genes score. All right. I'm not convinced with the name. We'll deal with that later. But this might be. Okay. Okay, I want to now to this would be now I want to do a plot where we have sort of the x-axis, the number of mutations, and then sort of this oops, sorry, I'm trying to, why is this messed up? Yeah, so x-axis number of mutations, and then the y-axis would be this excess gene score. All right, let's do this. Okay, this. Oh. Pa, 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 pa. Okay. Okay, let's do this. Okay, this is all right. Let's be a bit. Okay. Okay, this is kind of terrible, but this will work. Okay, this. Okay, perfect. Excess small. There's some, okay, item. Item, okay, you know what, okay, I think this is okay. Okay, this is kind of terrible, but this will generate the plot we want. Okay. Okay, this is absolutely terrible, but it will work. All right, so here it's the number of mutations, and this is the and now all we need to do, so we need to, if we find some decent thresholds, then this will wait, okay. Yep. Okay, I regret doing this. But this will work. We just guess. Let's see if it. Okay, we have a few minutes. Let's see if we can. So we've written down the main idea. That was very nice. Let's start cleaning up though. Start cleaning up. Okay, so this will. Right, let's get rid of that. Okay. What they call excess small gene square. Excess. Okay, this is alright. This is incredibly slow and atrociously badly done, but if it works, you have a starting point, and then okay, all right, there it is. Oh, let's actually let's. Nope. Plot. Nope. Oh. Okay. Yep, some. This work. So, all right, okay, right. We're a little bit running out of time. A little bit running out of time. So let's just. All right, let's just do this, and then we are going. Let's start wrapping up. Okay, we start wrapping up. Okay, we proposed this metric and implemented it. Plotted. For a few example species. Okay, all right, so this was great. I think once okay, this figure 20, so once we have the new updated figure, I think that will be it. Wait longer, and then all right, and then in the meanwhile, I am just gonna start wrapping up. So let's see. Okay, I do wanna add this this to the notes. The notes proposed. Okay, this might actually be right. We still need to show that this works and do more validation, but this was always one of the goals of this project is, can we turn this rough intuition into some sort of metric, right? Actually, maybe that was a little bit too. It was a little bit too quick to. Sorry. Right. Okay. So for the next two. We need to explore variations. For example, what is the best threshold for the z-score? For example, that's a good question there. What's the best threshold? Okay. Sorry, okay, I'm not. Let's. I forgot completely. Okay, I somehow mistakenly Okay, I'm rushing now a little bit too much for my own taste. Okay, so we still need to explore variations of this, but okay, I access small gene score. Not convinced with the name. We'll have to work with Chat GPT or DeepSeek. You know, that's the to figure out which one to use a better name. But for now, let's keep it as it is. And then so this code that I did today is pretty messy. So what I'm going to do is I'm going to put it in the work in progress in a few seconds. Let me fit. Okay, this is. And then, so next week we will all right. Oh, there it is. Yeah, this is. Oh, okay. Still need to work on this one. Number of mutations. This is wrong. I think I might have. Call it M4 for -4. Okay, now it's taking a long time. Let's see what. So we're getting gene positions. Okay. All right, so this whole gene positions parsing is probably slow, probably very slow. Probably should cache this. Okay, so now we're just waiting a little bit for this. Sort of messed up a bit the okay, I'm gonna, as I said, this code is pretty messy, so I'm gonna put it in this work in progress branch. So what I did, stash, merge, and now okay, and now I'm gonna put all the code there. Access a small gene score, and then plot ES versus number of mutations. Okay. Okay, it's something running. Okay. Yeah, so that's okay. Python's running. Oh, it's also using a ton of memory, which is probably why it's so slow, or part of the reason why it's so slow. Oh, there it is. Yeah, this is okay, there it is. This is I lost the window. There it is. I don't know why this is. Oh, here, did I mess? Oh, messed up here. Okay, I messed this up. Because this should have been, okay. Oh, okay, this was actually, okay. Okay, I messed that one up. Okay, it's gonna. Okay, today, all right, I really do want to see that. So we're gonna go a bit over time because I messed that up. So what I messed up was that the, okay. Oh, sorry. Yeah, this was really going up to 1,000. Okay, so this is, so I was looking at these crossings of these. So the dashed lines represent the initial values, but this was really only plotting a few values. So still, by 500 mutations, we're very clearly okay. Okay, I'm just gonna amend the commit. So and okay. Yeah, I think it's gonna take a couple of minutes here to process, but I'm pretty happy with today's progress. So we have now a concrete value that can be computed based only on the outputs of checkm2, and it will print out a number, and then we could use simulation to sort of what's the name, to benchmark, not benchmark, but to find the right thresholds and to benchmark the right thresholds and to fit a model so that we could go from this number, which doesn't mean much, like minus 600, whatever that is, like, oh, minus 6, we could go from this number like minus 400. Oh, look, minus 400 is pretty bad, up to minus. So we would have to tune this based on the data, but this could actually work. This could actually be a tool that you run on your genomes, and it uses the GMGC v1 all complete as a database and prints this. And then so let's just give it a couple more minutes. I will have to clean, so for next week, let's first of all maybe clean up the code a little bit. Maybe get rid of some of these older versions of stuff that we had, or figure out most of this can probably be pre-computed so that we're not computing it every time. Probably also figure out what other genomes we can use. So now we've been using this, 1, 2, 3, 4, 5, which frankly, it's just like, oh, what are good genomes? Oh, E. coli, and then like, I don't know, Bacillus, Staph aureus. Like, we could probably do a bit better. We could even start looking at mags. So let's do that next week. Let's do that next week. Start looking at the broader So next week we'll do these two things. Focus on cleaning up, and then looking maybe at a broader collection of genomes. Meanwhile, let's see here. Is there something here that I'm doing that will be very stupid? So get gene positions. Oh, there it is. Okay, yeah, this looks pretty good. All right, yes, this is it. This is, all right, there's an area of confusion. We might still be able to push this up with a little bit more cleaning. But this is a number. Some of these scores might below 4. We could try below 2. There's still some tuning here to do, some benchmarking. But this is very nice. Okay, I'm happy with this. I am going to push. Actually, what I forget. Let's see what this does. Yep, it pushed both the work in progress, the work in progress, and the main repository. So everything's on the repository. So I'll be also, I forgot last week to actually do a recap. Also, there really wasn't much to recap except me figuring out what to do. But this week there's a lot. This was maybe a big step. I'm pretty sure this is not the final version that we will eventually converge on, but I think this was good progress from sort of a rough idea to here's something that we can compute from a genome. It's a number. We can use existing genomes to benchmark that, and to tune and to find the right parameters for that. And I forget, there's a word I'm looking for here that I forget, and chat will tell me later. In the meanwhile, I forgot to play the intro music, but here's the outro music for everybody to enjoy. And so I'll see you next week. As usual, have a subscribe to the channel. Have a